Hello everyone, I'm Katie Contos and welcome to today's webinar, which is hosted by the Clean Energy Solutions Center in partnership with Enerdata. Today's webinar is focused on yes but no, adoption and rejection of energy efficiency innovations. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or over your telephone. If you choose to listen through your computer, please select the mic and speakers in the option pane. Doing so will eliminate the possibility of feedback and echo. If you choose to dial in by phone, please select the telephone option, and a box on the right side will display the telephone number and audio pin you should use to dial in. If anyone's having any technical difficulties with this webinar, you may contact the GoToWebinars help desk at 888-259-3826 for assistance. If you'd like to ask a question, we ask that you use the questions pane where you may type it in. The audio recording and presentation will be posted to the Solutions Center training page within a few days of the broadcast, and will be added to the Solutions Center YouTube channel, where you'll find other informative webinars as well as video interviews with thought leaders on clean energy policy topics. Finally, one important note to mention before we begin our presentation is that the Clean Energy Solutions Center does not endorse or recommend specific products or services. Information provided in this webinar is featured in the Solutions Center Resource Library as one of many best practice resources reviewed and selected by technical experts. Today's webinar agenda is centered around the presentation from our guest panelist, Mark Olsthorn, postdoctoral researcher at the Grenoble School of Management, who has joined us to discuss energy efficiency barriers that firms and households face in Europe. Before we jump into the presentation, I'll provide a quick overview of the Clean Energy Solutions Center. Then following Mark's presentation, we'll have a question and answer session where he'll answer questions submitted by the audience. At the end of the webinar, you'll automatically be prompted to fill out the brief survey as well. So thank you in advance for taking a moment to respond. The Solutions Center was launched in 2011 under the Clean Energy Ministerial. The Clean Energy Ministerial is a high-level global forum to promote policies and programs that advance clean energy technology, to share lessons learned and best practices, and to encourage the transition to a global clean energy economy. 24 countries in the European Commission are members, contributing 90% of clean energy investment and 75% of global greenhouse gas emissions. This webinar is provided by the Clean Energy Solutions Center, which focuses on helping government policymakers design and adopt policies and programs that support the deployment of clean energy technologies. This is accomplished through the support in crafting and implementing policies related to energy access, no-cost expert policy assistance, and peer-to-peer learning and training tools such as this webinar. The Clean Energy Solutions Center is co-sponsored by the governments of Australia, Sweden, and the United States, with in-kind support from the government of Chile. The Solutions Center provides several clean energy policy programs and services, including a team of over 60 global experts that can provide remote and in-person technical assistance to governments and government-supported institutions, no-cost virtual webinar trainings on a variety of clean energy topics, partnership building with development agencies and regional and global organizations to deliver support, and an online library containing over 5,500 clean energy policy-related publications, tools, videos, or other resources. Our primary audience is made up of energy policymakers and analysts from governments and technical organizations in all countries, but we also strive to engage with private sector, NGOs, and civil society. The Solutions Center is an international initiative that works with more than 35 international partners across its suite of different programs. Several of the partners are listed above include research organizations like IRENA and IEA, and programs like SE for All, regional focused entities such as ECOWAS, Center for Renewable Energy and Energy Efficiency. A marquee feature that the Solutions Center provides is a no-cost expert policy assistance known as Ask an Expert. The Ask an Expert service matches policymakers with more than 60 global experts selected as authoritative leaders on specific clean energy finance and policy topics. For example, in the area of energy efficiency, we are very pleased to have Dave Carey, Principal Harcourt, Brown & Carey, serving as one of our experts. If you have a need for policy assistance in energy efficiency or any other clean energy sector, we encourage you to use this valuable service. Again, this assistance is provided free of charge. If you have any questions for our experts, please submit it through our online simple form at cleanenergysolutions.org/expert. We also invite you to spread the word about this service to those in your networks and organizations. Now I'd like to provide a brief introduction for our panelists today. Mark Olsthorn, who is a postdoctoral researcher with a PhD in Business Administration from Grenoble EM and a Master of Science in Aerospace Engineering from Delft University of Technology. His research interests include adoption of energy efficiency and load management techniques. And with that brief introduction, I'd like to welcome Mark to the webinar.
Yes, hello. My microphone is on, I think.
Yep, you sound wonderful, Mark.
Welcome. Put on my screen.
Wonderful. Thank you so much.
Okay. Yes, hello, everyone. And thank you, Katie, for the introduction. And thank you all for tuning in today. I'd also like to thank the Clean Energy Center and Enerdata for the opportunity to talk on energy efficiency with you. Before I start my presentation, though, I first want to say a few words about the school where I work. Here you see our school. It's Grenoble École de Management. It's a French business school from Grenoble, which we say is the capital of the French Alps. You can see it on the map in the southeast of France. And the school was created in 1984, 34 years ago. And since then, the school has grown into an internationally recognized business school. We now have about 8,000 students who come to us from all continents for our leadership in technology and innovation. In the school, we have 8 research teams, one of which studies energy management, and that is the team that I belong to. Our team provides expertise on energy transition management, management of technologies, and their strategic implication for business and policy. Our approach is cross-disciplinary. We combine quantitative research in marketing and economics, where we use econometric analysis and field experiments, and qualitative research on business model innovation, relying on interviews and case studies. Our team is very international. We are, of course, active in writing scientific papers in European research projects. We also have a specialized master's in energy marketing and management, and extension activities are very important to us. We are in the process of developing a chair to develop practical knowledge for managing the energy transition, and to do that in collaboration with stakeholders. So if you're interested in collaborating with us, please write me an email or contact my colleague, Karine Sebi. You can find our contact details at the end of this presentation. They'll be shown on a slide, and later on YouTube you can scroll back to find them, or on Google, of course. Now that said, let's get to business. Yes, but no. The title will become clear in a few minutes, but the subtitle can give you a hint. It is about adoption and rejection of energy efficiency measures. This webinar will have 4 parts. First, I will introduce the general concepts of what is called the energy efficiency gap and the energy efficiency paradox. Then I will discuss 2 empirical examples from my own work. One is about finding explanations for adoption and rejection of energy efficiency measures. And the second one looks at the effectiveness of a policy instrument to promote adoption. In this case, the instrument is a subsidy. And finally, I will conclude with a brief macro level review of the progress made, and to answer the question, are we closing the gap? But let us first go back to the 1970s. Here you see a man's paint spraying sign saying, sorry, there's no gas. We're back in the middle of the oil crisis in the 1970s. It's these crises that made it felt how central and reliable supply of energy is to our ways of life. It showed that cheap, abundant energy cannot be taken for granted. And in reaction to those crises, the US government started championing energy efficiency as a multi-edged sword, a solution to many problems. It went so far as to equate energy conservation to patriotism, and said that each gallon of oil saved was a new form of production. This is just to show that energy efficiency emerged as a topic of political and academic interest in the 1970s, launched by the oil crisis. Several scholars supported the notion of energy efficiency as a win-win solution with huge unused potential. Here you have a quote by renowned energy analyst Daniel Yergin, who was at Harvard at that time, and he estimated that the US could consume 30 to 40% less energy and still enjoy the same or an even higher standard of living. And he continues, although some of the barriers are economic, they are in most cases institutional, political, and social. In other words, not much of a problem. And when the energy crisis was over, though, attention for energy efficiency soon faded. But it has made a comeback with a vengeance as climate change and financial instability and geopolitical tensions seem to meet. And 3 decades later, in 2009, McKinsey, important global consulting firm, still found that there was huge unused energy efficiency potential. And by then, it had become clear that the barriers are persistent. And not only in the US, there's unused potential. Because also the IEA, the energy think tank of the OECD, recently stated that a huge opportunity is going unrealized. It projects that 2/3 of the economic potential to improve energy efficiency will remain untapped by 2035. So that means we are suboptimal in terms of welfare. And this potential exists in all sectors, as you can see on this slide. So there seems to be a huge gap between what is economic and what is actually realized. So here we have a display of seemingly and persistently uneconomic behavior. We can say there's an apparent reality, something that you observe, that some energy efficiency technologies that would be socially efficient, so you can read net welfare increasing, are not adopted. That's what we call the energy efficiency gap. It becomes paradoxical, though, when we take a private perspective, because standard economic theory would expect consumers and firms to minimize costs. But much of the energy efficiency gap is said to come from the apparent reality that some energy efficiency technologies that would pay off for energy users are nevertheless not adopted. You could say they're leaving money on the ground. For economists, this is an empirical anomaly, or more popularly, a paradox. It is what is referred to as the energy efficiency paradox. The efficiency paradox is a narrower version of the efficiency gap, as you understand from these 2 quotes. So here we are. Yes, but no. Yes, that energy efficiency measure is profitable, but no, we do not adopt it. So the question we are then faced with is the following. So why do we stand here confronted, as Pogo said, by insurmountable opportunities? That's what Amory Lovins of the Rocky Mountains Institute wrote in 1976, after the first oil crisis. More formally, you can phrase it as follows. If conservation actions are rational, then why shouldn't governments simply wait for market forces to cause these actions? So this is a quote by Bloomstein et al., one of the first to academically investigate this apparent gap between reality and theory. So let's take a deeper look into the gap. So close to 4 decades have passed since first academic interest in this phenomenon, and those decades have produced many studies that offer answers to the question. So many explanations of why an energy efficiency gap exists or why there is a paradox. So let's dissect this phenomenon a little bit. Here in this graph, at the bottom, we have the current practice, so the baseline efficiency level. And higher up, we find the technologist economic potential. So that's what the IEA and McKinsey and Daniel Yergin calculated. It's the potential calculated based on the benefits and costs of available technologies given expected energy prices. So the potential optimal efficiency is even higher if we account for market failures in energy market. For example, if we take into account social costs caused by the use of energy that are currently not included in the price of energy, such as pollution and health effects, which we call negative external costs. So you could say the fair, between quotes, price of energy would probably be higher, which would make more efficiency measures profitable, so the potential increases. So now here we have the energy efficiency gap between the ultimate potential and the baseline. And here we have potentially a paradox between the private optimum as calculated by the technologists and the baseline. So there are different fields who offer different explanations for this paradox. So let's have a look at those explanations. First, there is the die-hard classical economists. There are not many, but they say that a paradox does not exist. And they say that there's little reason to think that households and companies invest suboptimally, that they are in fact minimizing their costs. They say they blame it on the calculations of the potential. They say that those are wrong, and that because they do not consider important costs and specificities of the energy users. So if you take a user perspective, the decisions are more or less optimal. Most neoclassical economists, however, say, well, energy users may indeed make cost minimizing investment decisions, and the paradox is much smaller probably than it may seem because of such errors in measurement and modeling. But there's evidence that markets for energy efficient products are not efficient, and that market failures exist that lead energy users to make decisions that are not in their firms or their personal best interests. So they cause privately and socially suboptimal welfare outcomes and would provide legitimate reasons for policy interventions. So what remains between the technologist's economic potential and the neoclassical economics potential is those errors in measurement and modeling. But with this explanation, there remains a paradox and a potential higher level of optimal efficiency investments. Okay, neoclassical economists stop here, but behavioral economists and organizational theorists turn their attention from markets to the actors, like households and companies, and say that consumers and organizations do not make cost minimizing decisions. They show consistent deviations from the supposed optimal behavior. So for example, so let's go there, here. For example, we tend to put more weight on the costs than on the benefits of an investment. It's called loss aversion. And such biases lead to suboptimal welfare outcomes. And these biases can also legitimize policy interventions. Interventions to, as some say, help consumers and firms help themselves. And this raises the optimal efficiency level some more, so we're a little bit higher. So now, and there still remain some errors in measurement and modeling, and a little gap between the technology's economic potential and the behavioral economists' economic potential. So the paradox, according to them, is a bit larger than according to the neoclassical economists, but not as large as initially it seemed. Okay, so now we have 4 steps between the ultimate potential and the baseline. So in the process, I've said that market failures and behavioral biases lead to suboptimal decision making, and that those would provide legitimate reasons for policy interventions, so not the errors. So we can try to raise the level of efficiency by eliminating those market failures and those biases using policy instruments. However, those policy instruments are rarely 100% effective, and they come with their own costs. So it only makes sense to employ the policies that are cost effective themselves. Because we cannot achieve the full behavioral economist's potential. Inefficiencies will remain, and modeling and measurement errors must not be corrected by policies. So if we eliminate what can be eliminated, the behavioral biases and the market failures in an efficient way, then we reach a higher level of potential, but still below the behavioral economics potential. And there remains a part that cannot be, that we cannot get at. So we have a narrow social optimum. If we then move beyond the private perspective to the social perspective, we can raise the efficiency level a bit more by correcting the market failures in the energy markets, and so raise the private optimum, which induces more energy efficiency investments. Okay, so now you got a theoretical understanding of the energy efficiency gap and the paradox. Now let's look at some practical examples for each of these steps. So between the baseline and the ultimate potential, what are examples of failures, biases, and errors? So here you see the 4 steps again on the left side, or in the middle column, and the errors, the market failures, the systematic biases, and the market failures in energy markets. And in the right column, I listed some examples of such errors, failures, and biases, which can act as what we call barriers to adoption of energy efficient technologies. So if you go to measurement and modeling errors, we see that they hold explanations for why the potential of energy efficiency and thus the gap is overestimated. For example, there may be hidden costs, such as overhead and transaction costs, and costs that are real. Those are costs that are real to the adopter, but that are hidden to the observer and not feature into the potential calculations. Or the heterogeneity of firms and households. So what is profitable for the average firm or household may not be profitable for all firms, so not all will adopt. Further, new technologies may entail more risk and uncertainty, because there's not much experience with those technologies yet, which would rightly cause caution in decision making. And they may also have inferior performance on non-energy aspects. For example, efficient lights are more efficient, by definition, but their tone used to be, at least until recently, less pleasing. So you can see that may cause a barrier to adoption. Now, if you go to markets for energy efficient products, we can see they may not work efficiently because of several reasons. For example, buyers may lack information on the technologies, and sellers may not know buyers' preferences, so there's imperfect information. Information can be asymmetric, where buyers and sellers do not have the same information and would, for example, make it hard for the buyers to judge the performance of an efficient product. Third, the buyers may prefer to postpone the adoption if they expect any cost reductions or want to learn from others who adopt first. So there's a learning by using effect. And finally, they have principal-agent relationships, which means that there is a mismatch in incentives between, for example, a landlord and a tenant. So where one makes the investment while the other enjoys the benefits. So one who making the investments may not have an incentive to do so if he cannot enjoy the benefits. Okay, then third, examples of behavioral barriers are loss aversion. I already mentioned that, which leads consumers to disproportionately weigh the investment costs against the benefits of reduced energy expenditures. So also leading to underinvestment. Attention may be biased. So information may be perfect, but may not be consumed or understood because the source is not trusted by the user. And finally, mainly in firms, rationality of firms can be bounded, in the sense they not have the time and resources to assess all information, and they have limits to the times and skills they have, leading to suboptimal investment decisions. And then finally, at the bottom, you see that market failures in energy markets, which can explain the difference between the gap and the paradox. So these may include the unpriced external costs of energy use, such as the environmental pollution and the costs, for example, to guarantee a secure supply. Correcting those will not change the social optimum, but brings the private optimum closer to the social optimum. All right, so that's the theoretical introduction. I hope it clarifies some of the, well, it helps you understand the energy efficiency gap and the energy efficiency paradox. I'd now like to present an example of research that we did into adoption and rejection of energy efficiency measures. And this is a research that focused on the commercial and services sector in Germany. It's a work that was published in Ecological Economics. You can find it there if you're interested in all the details. And the question we asked in this study was, how are adoption and barriers to adoption of energy efficiency measures related to the characteristics of the company and of the technology? So the first two blocks on the left. Normally there are 3 types of factors that can affect adoption, in addition to the organizational characteristics and the characteristics of the energy efficiency measure. There's also the context, but we leave that out of consideration. So we focus on organizational characteristics and energy efficiency measures. And these 3 relationships, so also want to see whether the effect of the organizational characteristics on the adoption and the barriers is affected by the technologies, basically, whether it depends on technologies. So how did we do that? We use a representative large sample survey among commercial and service sector firms in Germany. So we asked close to 2,500 firms about their adoption and reasons for not adopting if they hadn't. Now, why in this sector? Now, first, it's quite a large sector. So it comprises 16% of energy end use in Germany. And according to studies, there's a considerable efficiency gap in this sector of 141 petajoules. And this gap exists mostly in auxiliary building-related measures. So not in core processes, but in efficiency measures that are related to the buildings of these companies, which include such things as lighting, insulation, and heating systems. So those are the efficiency measures that we focus on. You see them on the right. Now we have efficient lighting, insulation, heating system replacement, and also more operational measure, the optimization of the heating system operations. So those measures are cross-cutting. It means they're not specific for any type of firm per se. They involve ancillary functions, so are not part of the core process of most firms, and they're heterogeneous. So they're different in nature, and yet not too specific. They all comprise some groups of technologies within which there's variation, of course. So what we do is we ask about adoption and barriers. So first we adopt, did you adopt in the recent past? Now, if they say no, we ask, did you consider? So we're going to find firms who actively rejected the adoption of these measures. So, because if they say yes, we did consider, but no, we did not adopt, we know, okay, they made a decision to reject. And then we ask which of 13 barriers they thought were relevant to their decision. And then we also ask about other factors that we want to relate to this decision. First of all, there are factors related to agency. So to get at the principal-agent relationships, and factors relating to absorptive capacity, and in this case, energy-specific absorptive capacity, basically energy-related knowledge. All right. So then our research model becomes, or at least the part that I'm going to talk about today, it looks like this. So we look at the organizational characteristics and their effects on the probability of adoption first. We split the organizational characteristics in 2 groups. First, we look at the agency factors. So is there a case of split incentive? So is the decision made in a different part of the organization than where the energy costs are paid, for example. And we look at absorptive capacity. So it's the capacity of a firm to acquire, absorb, and transform knowledge into value, basically, which is dependent in this case on their prior knowledge of energy and energy-related issues. So within the agency factors, we have 3 variables or proxies that we use that represent agency factors. So first, whether there's ownership of the building, so whether they are renters or not. At a level below that is their ownership of the energy supply equipment, in this case the heating system, and is the firm in question a subsidiary or branch of a larger firm, and this may be a source of split incentives. Within the absorptive capacity factors, we look at energy management variables. So for energy, is there an energy manager? Is there an energy management system? Have they had an energy audit to assess if there are profitable energy efficiency measures in their company that they could take? And whether they are currently using renewable or clean energy. So these are factors that would suggest a higher level of energy-specific knowledge, which we would hypothesize would make them more aware of the benefits of energy efficiency and thus have an effect on the adoption. Okay, now let's see what we got from in the results. Yeah. So here we have the results of the probability of adoption. So this is a complex table, but you see here the variables on the left side. So the numbers tell you whether there's a positive or negative relationship with the probability of adoption. So first look at the technologies. So for lighting, for example, we see that the probability of adoption is higher than for heating operations. So that's the base category, that's where we have to compare to. And for insulation, you see that the rate of adoption is lower than for heating operations. So this basically reflects the turnover rate of these technologies as well. Now, let's look at the agency factors here below. So the red tells you the relationship is negative and statistically significant. So for all these agency factors, we see that there's a negative relationship with adoption, as we expected. So if the firm is a tenant, so renting its spaces, he's less likely to adopt energy efficient technologies. Same if the heating system is external to the firm, so they have no control over it. And also if the firm is a subsidiary, it's more is less likely to have adopted in the past energy efficiency technologies. So that goes, that's evidence in support of our expectation. If we look at the absorptive capacity factors, we have significant results for the environmental and energy manager, whether they had an energy audit and whether they had used renewable or using renewable or clean energy. And these relationships are positive also as we expected. So here we have support for the positive effect of energy specific absorptive capacity of a firm. Okay, so that's cool. But now if we look at the individual technologies, so lighting, insulation, heating replacement and heating operations, each in its own column, it's a more complex pattern. For example, if you're a tenant, the heating operations adoption is much less likely, but not necessarily for the other technologies. So this could be interesting. We could explain it by heating operations. It may involve some adaptations of the system, the heating system in the building. That's not the heater itself, which is more tied to the building itself, which the tenant has less control over. So that's one possible explanation. If the heating system is external, you have no control over it. It has effect over adopting energy efficiency measures related to heating, but not to lighting and insulation. So that makes sense, etc. But overall, the pattern is in favor of our hypothesis, and that the absorptive capacity helps, know that the presence of agency problems could cause lower rates of adoption, or it's could. Then in below there you see, for example, if you look at energy audit, that's an interesting one. It has a positive effect on adoption of all different technologies, so that adds to the evidence that that already exists, that energy audits could be an effective tool for promotion of energy efficiency adoption. All right. Okay, now let's have a, the organizational characteristics have an effect on the adoption. Now let's look at the barriers. So what reasons exist for not adopting? Now here it's a very complex slide, or very small small letters, but it's not too complicated. So here we have the 4 technologies, so lighting, insulation, heating system replacement, and heating system operation. For each of the technologies, it lists the 13 barriers we asked them about, and which percentage said, yes, this is a relevant barrier. And the order of the barriers is the same in each of these graphs, and you see the pattern is quite similar as well. So the reasons for rejecting these technologies is not so technology dependent, it seems. And you see one stands out quite significantly, and that's that the spaces are leased or rented. So signaling a landlord-tenant issue. Further, you have too high investment costs as an important barriers, and the fact that there are other priorities. The firm has other priorities than energy efficiency. I'll talk more about that later maybe. But you see that the pattern is quite significant, and you also see at the bottom end risk for quality of the product, and risk for the production process, for interruptions of the production process is not so important. Well, it makes sense because we're not talking about technologies that are directly related to the production process. Okay. Now, we also related the organizational characteristics to the landlord-tenant barrier. So, which organizational characteristics, the same as we just saw in the other table, have an effect on the likelihood that a company reports landlord-tenant as a barrier. So, if we look at the technologies first at the top, you see that there's only effect for lighting, and it's negative. So, for lighting, if we're talking about lighting, the likelihood that a company mentions that the fact that their spaces are rented is a barrier is less likely. That makes sense. Lighting is less attached to the building, and often tenants can change it, so they have control over it. But the other technologies, it's less the case. Now, what can, if we look for guidance on what can relieve this barrier or make it mitigate it, we look at the tenant thing. No, it's not quite the case. Of course, the tenant suggests there's a positive relationship with this barrier, and it tells us that if you're a tenant, you're very likely to run into this barrier. And on top of that, regardless of tenancy, if heating system is external to your firm, and if you have no control over it, you're also more likely to say this is a barrier. That adds to the problem of tenancy, I'd say. In the orange variables, the absorptive capacity factors, we see that the energy audit here reduces the likelihood that the fact that spaces are rented is a significant barrier. So that may be an instrument that can help overcome this most significant barriers that we identified. So okay. So to conclude this study, we see that the organizational characteristics have effect on adoption, so that there is a relationship. So agency problems, whether they're external, if your spaces are rented, or internal, if you're a subsidy, can hinder adoption of energy efficiency measures. And they also can be technology specific. So if you're talking about the heating system, If you're not a tenant, but the heating system is external to your firm, because you are a small firm and you share the building with other firms, and the heating system is central to the firm, you run into the same problem. And we also see that the energy knowledge resources, so the energy-specific absorptive capacity, is associated with higher adoption. Now, on the barriers, we identified the most relevant ones, which is the owner-user dilemma or landlord-tenant dilemma, the investment costs, and the other priorities that the firms have, and the least relevant is the technical risk of the barrier. So that's what can we learn from it that has some implications for policy. So first of all, how can we overcome the agency problem and the split incentives between landlord and tenants and subsidiaries and mother companies? Well, we can make use of communication devices to reduce the information asymmetries. And we saw that energy audits might be effective in doing so. Energy and eco-labeling is also used to overcome such barriers. And it has been shown before that eco-labeling can indeed be a communication tool that makes potential renters of commercial spaces willing to pay a higher rent for the building, so that can be effective. Another way to do it is to overcome the split incentives is to bundle the risk and rewards in a separate entity like an energy service company. Okay, now if we look at what can enhance the ability to acquire, assimilate, and exploit energy-related knowledge, that increase the absorptive capacity, we again can look at the audits. To enhance the awareness of the firm, so it learns from having an audit what is possible within the firm. The EU is already requiring this from I think especially larger firms, and encouraging it for smaller firms. Then for larger firms, you can also promote energy management, but it may be a bit over the top for smaller firms. But for smaller firms, ESCOs may be able to provide a solution. They could provide scale where it doesn't exist by aggregating very small quantities. All right, that was the first study. The second study is a bit shorter. Now let's look at what a subsidy can do for residential energy efficiency upgrades. So we're moving to households, and we're specifically interested in the effect of free riding. As we know, many companies or many governments and also utilities use subsidies to promote energy efficiency upgrade, but the effectiveness of subsidies is often overestimated because there are such effects as the rebound effect, moral hazard, and postponing adoption when you think a subsidy is coming, and free riding. So using the subsidy when you actually don't need it. So these free rider estimates are quite important, and usually when you look at subsidy programs after they've been implemented, you find large variation in the amount of free riding, but typically above 50%. So 50% of those who enjoy the subsidy would not have needed it to adopt. So that's a huge inefficiency. But of course, you want to know before you implement the subsidy what you can expect in terms of free riding. So here we use data from a household survey in 8 EU countries. So you see the number of respondents in which countries investigated. It's part of the research within the Horizon 2020 Brisky project. It's EU funded. So we look at households. The surveys are representatives, and in total we have 10,000 respondents. So we propose them a hypothetical heating system replacement. So, but first we ask, are you planning to replace your heating system in the next 5 years? If they say yes, we say, okay, stop the survey, because they would adopt anyway. We can say they are free rider. So if a subsidy is implemented, they would enjoy it, but not have needed it. Now, those who say no or don't know could be incited to adopt with the subsidy. So they enter into a choice experiment in which we offer a hypothetical heating system, which is a bit more efficient than the current one, and we say that it costs 2,000 euros and it would save them a total amount of X euros over T years, and we vary those amounts. Now, if they say yes, we adopt, we know they are also probably a free rider because we have not offered a subsidy yet, but it just needed to be confronted with these with this offer. So that's what we call an observed weak free rider. If they say no, then we offer them a subsidy, and if they then adopt, they are an incentivized adopter, so they react to the subsidy, and their level of subsidy that they would need to adopt would be between 0 and this level of subsidy. And if they say no, they are non-adopter, and their subsidy would be at least higher than the level that we offered. So now we can estimate the distribution of the threshold subsidy of the in households in those EU countries. So we assume that this is a normal distribution, and we fit it to the data. And then first we do this for all countries combined, and then we see that the mean and median threshold rebate, so the level at which half of those in the experiment would adopt the heating system, is 775 euros. But you see that there's a significant part that extends below 0, and these are we call free riders. Their threshold subsidy would be well, less than 0. So those we call weak free riders. They did not say that they have plans to adopt, but confronted with the offer, they say, yes, we adopt. All right. Now, if we do that for all countries, we see consistently high levels of median subsidy. So remember, the heating system itself was priced at 2,000 euros. So these subsidies are close to, well, somewhere between, some are very low in Poland and Romania, some very high in Sweden. So 40% or so of the total cost of the heating system, with considerable variation. Now we can use this information to see what is the share of free riders that we expect for any level of subsidy. Now here we have subsidy levels on the horizontal axis. It's the same for each of these graphs. Between 0 and 1,000 euros. 1,000 euros is half of the cost of the heating system. And the solid line tells you the total share of free riders. So the strong free riders and the weak free riders. Now you can see that in all the countries it's quite high and remains above 50%, even at 1,000 euros subsidy. Yeah, you can see it's highest in Germany and Italy and lowest in Romania. Okay, so it's quite significant, and you can also see that the share of weak free riders, that's the dashed black line, is higher than the strong free riders. So it's a large amount. Except for Romania, there's the inverse. It's a large share of strong free riders, but in Romania something special is going on. They are currently in the process of updating old inefficient central heating to more modern systems. So it's a special case. Okay, conclusions. So with the choice experiments, we can get an estimate of free riding before implementing a subsidy, and the numbers correspond quite well credibly with the numbers that you get from evaluating free riding after the subsidy. And the free riders make up a large share of the expected beneficiaries. So it's more than 50% at a rebate of 1,000 euros. So that makes such a program much more inefficient. We can find relatively high rebate estimates across the board. So premature replacement is not something people easily do. They need quite some money to incite them to, compensate them for their capital loss. And we also saw that the subsidy itself, or the offer of a subsidy, may function as an information device, which causes potential households who would not have needed a subsidy to adopt and still enjoy the subsidy. So in terms of implications, yeah, so the first thing I already told you, the free riding makes subsidizing heating systems upgrades quite expensive, but we also see that the differences between countries. So if you can coordinate between countries and you can target those countries where the efficiency is highest, and then progressively go forward to the other countries where it's less efficient, depending on how much your target for energy conservation or greenhouse gas emissions is. Well, in a European setting, that could be possible. Okay. So those are two examples. Now I'm reaching the conclusion. So I'm not the only one doing this research, so many other people are looking at the same kind of questions, but in different setting with different technologies, different countries, different users. But still, and this yields practical policy advice. But still today, and more than ever, governments and energy experts are still touting energy efficiency as a win-win, as a motor for growth and job creation. So there's the European Commission, for example, says that the review of the energy efficiency legislation unlocks the energy savings that can boost growth in the US economy. So energy savings have been locked. So 50 euro bills have been lying around behind the barriers that we've so far failed to remove. So there's still a gap despite all this work. So one may wonder that after 4 decades of energy efficiency gap, what have we been doing? Should the conclusion be then that the energy efficiency gap is not an anomaly, but a defining inseparable characteristic of energy efficiency, that we have to accept it? I think not. I think you have to realize that the diffusion of innovations is always gradual. So reality is inevitably behind the current optimal level, and assessments of efficiency potential do tend to be too optimistic. But I'd rather say that 4 decades of research have improved our understanding of the diffusion of energy efficiency measures, and that the sustained gap is a sign of both ongoing innovation and plenty of open questions for research. So, but if we get desperate, we can call the IEA for consolation. The IEA is keeping a finger on the pulse of energy efficiency progress. Yeah? So it sends a positive message. It said that in its member countries, which is most OECD countries, energy consumption has been decreasing for 10 years already. And consumption is no longer following GDP. So here in this graph, the economic activity, which you could relate to GDP, is the upper graph and the upper line, upper curve, the activity effect. So that's growing, but the total final energy consumption is this orange curve, which has been decreasing over the past 10 years. And so, and largely due to the efficiency gains made. The green curve at the bottom. So consumption seems to be no longer following the GDP. So 2/3 of this decoupling is allocated to the efficiency effect. Now, of course, well, GDP and energy use are still coupled. Of course, more GDP leads to higher energy consumption, but the multiplication factor has decreased fast enough to keep the energy use flat while the GDP rose. And so that is good news. But this analysis excludes big emerging economies and cannot disprove that adoption rates of energy efficiency are still suboptimal. So the work goes on. Work is never over. Improvement in global energy efficiency slowed down dramatically in 2017 and was broadly caused by an apparent weakening of the efficiency policy coverage and its stringency, and by lower energy prices as well. So you can see in this graph how much global energy intensity improved each year. And you see that in 2017, it was much lower than in the previous years, and about half of what would be needed to be consistent with a 2 degrees target. So consistent with the Paris Climate Agreement. And efficiency improvements in 2017 were also not sufficient to counteract the effect of higher economic growth. So it is in 2017 it led to an increase in global energy-related carbon emissions. So we have weaker coupling, not per se decoupling. So closing the gap means increasing the effort and sustaining the effort. Okay, so from my perspective, I can see three ongoing emerging trends for energy efficiency research. First, probably there will be more emphasis on policy evaluations. So they're increasingly relevant and urgent. We want results, but also data availability is growing, and the heterogeneity of the measures and the users limits the transferability of policy evaluations to other settings. So it's work that needs to be repeated over and over again. And finally, management will become more a focus. So from a management school, that's interesting. And so the boundary between the supply and demand side of the energy system is blurring. So if you have solar panels and wind turbines, they make consumers become prosumers, as my colleague told you a few weeks ago. So producers and consumers of energy at the same time. And demand response, so load shift, load management is coming up. And that is interacting with energy efficiency. So energy management is coming to the micro level, to the level of households and firms. And besides many efficiency measures are behavioral or operational, so not technological. So this puts the focus also on behavioral and managerial aspects. So energy management is likely becoming more strategic, and the capabilities of many firms to manage energy use are still underdeveloped. So there's something to gain. So the work is never over, but I'm hopeful that one day governments can stop championing energy efficiency, and that we may be studying an inverse gap, and that profitable energy efficiency measures have been exhausted, but adoption continues, and that we can say no, but yes. Just kidding, that would be inefficient. But thank you very much for tuning in. If you want to learn more about us, here you have the link to our website and our contact details. So please be in touch.
Wonderful. Thank you, Mark, for that outstanding presentation. As we shift to the Q&A, I just want to remind our attendees to submit the questions using the questions pane at any time. We'll also keep several links up on the screen throughout for quick reference to point to where you'll find information about upcoming and previously held webinars and how to take advantage of the Ask an Expert program. Our first question, we have a couple of questions to ask for the remaining of the time. Mark, our first question is, you showed what was the most important barriers for companies in the commercial and service sector. What can you say about households and their barriers, and what are the main barriers that keep them from investing in energy efficiency?
We talked about the commercial and services sector, and we saw that the landlord-tenant dilemma, so the problem of renting spaces, is a major barrier, and that holds for households too. So in many countries, 20 to 50% or so of the households are renting their residence. So also there you have the landlord-tenant problem. That's a big issue, and it matters what is provided with a rental home, and it also varies. So if the appliances are included, which is the case in some countries, when I lived in the US, for example, the fridge, etc., was part of the apartment, then the split incentives apply to those as well. So, and that adds to the dilemma, in addition to the equipment that is fixed to the building. So the split incentives is a huge one, and furthermore, the attention biases are major obstacles. So when it comes to appliances and cars, for instance, people tend to give no or very little attention to energy costs. So all attention is on the investment. So to a certain extent, it makes sense. So energy is not often a very large share of a household's budget. So they don't have much attention to the costs. So But we now have energy labels to help consumers take into account those energy costs. Like in the US, you have Energy Star. In Europe, you have these energy performance certificates, and they work. And they work almost too well, in the sense that people use them as a decision heuristic. So they base their decision on the label color and do not pay attention to the differences among the appliances within the same label color. So, and then you get the effect that the manufacturers have no incentive to go beyond the minimum level of what is required to get a good label color. So that, and there's another effect of this attention bias. For example, the metrics that are used matter as well. So for cars, for example, there are studies that show that the miles per gallon metric is counterintuitive. So people intuitively associate larger numbers with higher fuel consumptions, so less efficiency. Well, there's of course the reverse. So you can say for households, you have split incentives and attention biases that are important barriers. I'd say you can say that those are the most important, or at least very important.
Thank you, Mark. And I think we have time for one more question. The percentages of free riders you mentioned during your presentation was really high, surprising. If free riders make subsidizing energy efficiency upgrades so much more costly, why is it quite common to use subsidies to promote efficiency?
Yeah, it's a very good question. I think that in theory, subsidies can be efficient, but it depends on the situation. You have to realize that our study involved a rather marginal efficiency improvement and normal households who did not have a very new heating system. So they were among, you could say, the more likely to be convinced to upgrade. So the potential for free riders was quite high there. However, it can be effective, maybe even necessary in situations where people have not shown any adoption, have been failing to upgrade, and where there are many potential social benefits to capture as well that help to justify the subsidy. And so, for example, among households with little means who live in leaky houses, which in the French have a nice word for that, they call it energy calendars. So in those places, the investment costs are just prohibitive for poor households. But the potential gains are quite large. So there the risk of free riding is low and the potential social benefits are quite high. So there's much to gain. And a better insulated home on top of more efficiency and reduced energy costs could also reduce the health issues and improve the well-being and possibly the productivity of its inhabitants. So that would save on other social costs and would add to the justification of such a subsidy. So you can see, for example, programs which use this approach. So subsidies for renovation, for example, are often targeted to households who are trapped in poverty. In the US, you have the Radicalization Assistance Program, for example, who does that, and in France, you have the French renovation policy, which also prioritizes houses that you could say strain energy, and so where most benefit is expected. So targeted subsidies can still be can still be efficient.
Great, thank you again. On behalf of the Clean Energy Solutions Center, I'd like to extend a thank you to Mark and all our attendees for participating in today's webinar. We very much appreciate your time and hope in return that there were some valuable insights that you can take back to your ministries, departments, and organizations. We also invite you to inform your colleagues, to those in your networks, about the Solutions Center resources and services, including no-cost policy support through our Ask an Expert service. I invite you to check the Solutions Center website if you'd like to view the slides and listen to the recording of today's presentation, as well as previously held webinars. Additionally, you'll find information on upcoming webinars and other training events. We are now posting the webinar recording to the Clean Energy Solutions Center YouTube channel. Please allow about a week for this to be posted. Finally, I'd like to kindly ask you to take a moment to complete the short survey that will appear when we conclude the webinar. Please enjoy the rest of your day, and we hope to see you again at Clean Energy Solutions Center events. This concludes our webinar.